Hello friends, so we are gradually moving into the interesting aspects of thermodynamics. So even though so far we have been largely confined or discussing mostly the theoretical aspects, we have been introducing several terminologies, we have been looking into several distinct relations. We are gradually moving towards employing all the different concepts that we have learned to the systems we are interested in. So far we have considered what thermodynamics means, what a framework of thermodynamics involves. We saw the first law of thermodynamics and we looked into the second law of thermodynamics. Now one theoretical construction that helped us understand the second law of thermodynamics is the Carnot cycle, and we have spent quite some time in understanding the Carnot cycle. So what essentially Carnot cycle involves is, Carnot cycle is rather a theoretical representation of the heat engine, the operation of a heat engine. Now the heat engine, if you recollect, it is a physically available equipment or a machinery that operates in the framework of thermodynamics. So in thermodynamics you have heat transfer and work that is being done. So heat engine also operates in the same framework, so that is something that we could always relate to. Thermodynamics being a theoretical study, one place wherein we can, one physical instance wherein we can easily relate ourselves is to that of the operation of the heat engine, and this operation of the heat engine, the principal components of it are being represented in the Carnot cycle. So just for our recollection, the Carnot cycle rather it involves, or what it does is it replaces all the complex variables that govern the operation of the heat engine into pressure and volume. And by now you would have got more acquainted with the operation or the construction of the Carnot cycle, because we are considering it more than, or we have been considering it more than once in each and every lecture. So I hope this is the last time we go back to our understanding of the Carnot cycle, and from this lecture onwards we will be considering just a simplistic form of it. So yeah, this being the last time, let us begin. So what we have is, we have a system that is held at a state, or that is present at, or that is a stable state A, and you are imposing, or you are exposing this system to a source, that is which we refer to as the reservoir, that is held at a temperature T1, and from this reservoir there is a transfer of heat Q1 into the system, and now because of this transfer of heat, the system is moving from one stable state to another stable state, so A to B, and after reaching the stable state B, what we allow the system is to change its temperature from T1 to T2. So there is an non-isothermal transformation and the system changes to state C. Now at state C, what you do is you allow the heat that is lost during the operation of the heat engine, and you remove that specific amount of heat and you transfer it to, or you remove that specific amount of heat by making the system in contact with a reservoir, a lowest temperature reservoir that is held at temperature T2, and this allows the transfer of heat from the system to the reservoir. So ultimately you end up, or the system moves from state C to state D. So these are things that we have already considered, and now in order to establish or move back to the initial state, we compress the system so that we go back to the initial state, and thereby establishing a Carnot cycle. Now, so the change in state from A to B and C to D, they are unique and they share certain features. So first feature they share is their isothermal changes. So there is no change in the temperature here, it occurs at T1, this change occurs at T2, and similarly they are non-adiabatic, meaning there is a transfer of heat. So in contrast to the change in state from A to B and C to D, you have the change in state from B to C and D to A, and here there is, when the system changes from state B to C, there is a change in temperature from T1 to T2, and as the system changes from D to A, there is a reverse change in temperature from T2 to T1. So essentially here, these B to C and C to D is a non-isothermal change, but it is adiabatic in nature because there is no heat transfer that is involved. So essentially, when we are focusing on the change in the state of the system that is brought about by the transfer of heat, then all we need to consider is these two changes. And when we consider the changes that is brought about by the temperature or by the heat transfer, we need to also understand that these changes are not occurring at an isothermal temperature. So, or they are not occurring at a single temperature. So, we have changes that is brought about by a heat transfer. However, these changes are not occurring at the same temperature, they are occurring at two different temperatures. So, one change is occurring at T1. So, we have changes A to B and B to C occurring at, or rather A to B and C to D. So, these are the two changes that is brought about by the heat transfer. So, the transfer of Q1 brings about the change in state from A to B. The removal of heat Q2 brings about the change from C to D. However, in addition to this, it is important for us to note that the A to B transition, it occurs at temperature T1, whereas the C to D transition, it occurs at temperature T2. So, A to B occurs at T1, C to D. A to B occurs at T1 and C to D occurs at T2. So, whenever we want to quantify, so in this case we have changes that are brought about at two different temperatures. So, in order to quantify these changes, we take the ratio of the heat transfer at that specific temperature wherein the changes occur. So, there is a heat transfer that is occurring, and because of that there is a change in the state of the system. In order to quantify the change in the state of the system, we include the characteristic temperature during which the change in the state of the system occurs. So, therefore, the way we quantify the change in the state of the system when there is a Q1 and when there is a heat transfer occurs, so that we quantify by considering the ratio of the heat transfer and the temperature at which the system exists. So, therefore, the change in the state of the system, when the system moves from state A to state B at temperature T2, and this change in the state of the system is because of Q1. So, this change in the state of the system, the changes that is brought about from A to B, is quantified as Q1 by Q2, or rather Q1 by T1. And similarly, we have a change in the state of the system that is brought about by the removal of heat, but this change does not occur at T1 but it occurs at T2. It occurs at its own temperature, it occurs at its characteristic temperature. So, we cannot just say that change occurs because of this heat alone, because we need to consider this occurs at two different temperatures. So, we need to consider the characteristic temperature at which the system is changing its state. So, therefore, the change that occurs when the system moves from C to D is referred to as Q2 by Q1. Now, in the previous lecture, we saw that when we consider the operation of this Carnot cycle, wherein the change that is brought about by the heat transfer at characteristic temperature, and when we equate the efficiency that is associated with this operation, then we saw that these are related. So, this is Q, T2, pardon me, this is T2. So, the change that is associated with the intake of heat is equal to the change that is associated with the removal of heat. So, in the previous or the one before that, we saw one of the critical relation that we could derive from the operation of Carnot cycle is this: Q1 by T1 is equal to Q2 by T2, and this means the change that is brought about when the system intakes Q1 heat at temperature T1 is the same as the change that is brought about when the system loses Q2 heat at T2, and that is what this expression helps us understand. So, now this whole Carnot cycle, the changes that occurs in this whole Carnot cycle can simply be represented by this curve here, the cyclic process that occurs during the Carnot cycle, the cyclic change that occurs during the Carnot cycle that is exclusively brought about by the heat transfer can be expressed in this manner. And we need to understand that these two occur at two different temperatures, and that's the reason we have temperatures, that's the reason we are expressing this change in this specific manner. So now we are able to express the change in the state of the system in this way. So we are exclusively considering just the non-adiabatic aspect of the change on the state of the system. So the system starts at A and there is a heat that is fed in, and this system is at temperature T1 and there is a specific amount of heat that is fed in, and there is a change in the state of the system from A to B. Now the system is at temperature T2 and there is a removal of specific amount of heat, and this brings about a change, and both these changes are equal, and therefore we end up where we started with. So essentially what we have arrived at is a cyclic process because we have ended up where we started with. And secondly, whatever changes we have made by feeding in Q1 at T1 has been reversed when we removed Q2 at T2. So what essentially we have is a both cyclic and a reversible process. So we have a system at A that is at temperature T1 that moves to, when we feed in a specific amount of heat, system moves to B, and at B, which is at a different temperature, you remove a specific amount of heat Q2, the system moves back to A. So essentially you have established a cyclic process. You move to a place and get back to its original place. So such a cyclic process. Now when you consider the change, the way to quantify the change is the ratio of heat transfer and the temperature at which the system is engaged. So when the system is at A, the temperature is T1, the heat transfer is Q1, therefore the change is Q1 by T1. Now when the system is at B, the temperature is T2 and the heat that is removed is Q2 by T2. The change that is brought about by the removal of the heat Q2 is Q2 by T2, and we have seen that Q1 by T1, the heat that is the change that is brought about by the input of heat, Q1 by T1, the change that is brought about by the input of heat is similar to or equivalent to the change that is brought about by the removal of heat at Q2 heat at T2. So essentially whatever changes we have brought by the feeding in of heat has been reversed by removal of heat. So what essentially we then have is we have both a cyclic and a reversible process. Now we can easily rewrite this reaction as Q1 by T1 plus Q2 by T2 minus of Q2 by T2, and this will be equal to 0, and this minus sign here is because of the convention. So we have considered a cyclic process and we have arrived at a relation, and now this relation can be generalized in such a manner so that the summation of all the steps that are involved. So you have a cyclic process, a reversible process, cyclic and a reversible process. The system is going through several changes. However, all the changes, despite all the changes, the system is getting back to its original point. In that case, whatever changes that are brought about by different steps, when you sum it up, of course, following the right convention, then the sum of all the changes will be 0. Now it is important for us to understand this is not the feature of the cyclic process alone, this is a feature exclusively or largely because of the reversible nature of the process. So whatever change that is brought about by one step, it is being reversed by another step. So whatever change that was brought about by the heat that was fed in, it was reversed by the heat that was let out by the system, and that's the reason you end up with this relation here. So therefore, for a reversible process, irrespective of the number of steps that are involved, these steps, they reverse the overall change. Therefore, the system gets back to its original state. So therefore, there is not much change in the state of the system. There is no change in the initial state of the system. So therefore, the criteria that dictate the reversible process is the sum of all the changes that is described by the ratio of the heat transfer and the appropriate temperature is 0. So we are expressing the change as the ratio of the heat transfer at the appropriate temperature. Now when you sum all these changes, when you sum up all these changes for a reversible process, then sum of all will be equal to 0. So that is the characteristic feature, or that is the characteristic criteria for defining a reversible process. So whenever you consider a reversible process, whenever we are talking about a reversible process, the reversible process will be the one criteria to ensure that the process that you are viewing is a reversible process is that whatever change that occurs should be completely reversed. And since the change that occurs is described as the ratio of heat transfer and the temperature, this criteria should be satisfied. So it is this criteria that characterizes, or only if this criteria is fulfilled, we refer to a change as a reversible change. We refer to a process as a reversible process. Now, this ratio is nothing but this. We have come across this ratio in our previous lectures as well, and this ratio is nothing but the entropy. And therefore, what essentially we have is we have the summation of entropies at each and every change in the state of the system. We have specific changes in the state of the system, and we are summing up all the change in the entropies. So what we essentially end up having is the summation of the all change in the entropies during the reversible process. So this is a reversible process is equal to 0. So the change in the state of the system, which is the ratio of the heat transfer and the temperature at which the system is held, is nothing but the description of the entropy. And now in the description of the entropy, we arrive at, for the reversible cycle, we see that the overall change is 0. So whatever change occurs at each and every individual step is subsequently reversed. So that is the description of the reversible process, and that reversible process and that reversible changes means the summation of the ratio of heat and temperature should be 0, and that also means that the smallest change in the entropies during each and every step, and when you consider the smallest change, they get cancelled out, and ultimately the sum of all the smallest changes in the entropy that occurs in each and every step should be 0. So this is another criteria for describing a reversible process based on the entropy. The overall change in the entropy for a reversible process, which is equal to the sum of all changes at each and every time, each and every step, is 0. So this sum of all changes at each and every step is nothing but the ratio of the heat and temperature, and which is nothing but, or which conceptually it talks about the change that is experienced by the system. So essentially, from the very description of the reversible process, that is all the changes that occurs in the system is reversed, we are able to arrive at the criteria. So that criteria states that the overall change of entropy during a reversible process is 0. And again, we are able to arrive at this from the basic description of a reversible process. We have considered a simple example, and from that simple example we have been able to arrive at this particular criteria. So whenever we talk about a reversible process, we need to ensure that the overall change in the entropy is 0. Only then the process that we see is a reversible process. Now, at the end, towards the end of that previous lecture, we saw that this summation can even be refined and expressed as the closed loop or the closed integral of the change in the entropy, and this closed integral, which again represents the summation of the change in the entropy for each and every step during a process, is equal to 0. So whatever changes that occurs during the cyclic or during the reversible process is being quantified as the smaller or the entropy change at each time steps or each event or each process. So you have several steps that are involved that constitute a given process, and in that for each and every step there is an entropy change, and when you sum up all these entropy change, it completely cancels out, and ultimately the total entropy change is 0, and this is what a reversible process means. Now when you keep on reducing the width of this different events, the width of this different steps, then the summation can be replaced by the closed integral. So the closed integral meaning we end up where we started with. So in this condition here, this criteria here can be expressed in this manner. Now let us go back to the simplified corner cycle that we have. So we start at the state A and we move to state B by transferring a specific amount of heat, and this is carried out at a specific temperature T1, and we remove the heat Q2 and we go back to the initial state A. Now when you consider the change in the entropy, the overall change in the entropy, so here at state A, let us consider the change in the state from A to B. So at during this step, that is the change in the state of the system from A to B, the difference in the entropy, that is delta S A B. So we have a system that is changing from state A to B. The difference in the entropy would be SB minus SA. Now what essentially we have is, we have a system that is changing from state B. So this is the first step. Now in this reversible process there is a second step, and here we have the system changing from state B to state A. So the corresponding change in the entropy when the system moves from state B to state A will be SA minus SP. Now the overall change in the entropy during this process, that is during this cyclic process or during this reversible process, is nothing but the change in the state of the, or change in the entropy when the system moves from A to B, plus the change in the entropy when the system moves back from B to A. Now when we do that and when we sum this all up, these two gets cancelled out, and ultimately you end up with the criteria that we have already arrived at. So when you, just by considering the cyclic process, you are able to arrive at this same criteria that we have here. So however, there is one key point that we can take from this simplistic consideration, or rather straightforward consideration here. So what that is, when you consider the change in the state or change in the entropy, what we have considered is just the difference in the entropy at B and the difference in the entropy at A. So essentially, when you consider the change in the entropy, all you are considering is the difference at the endpoint and the difference at the initial point. And the same goes for the reverse process. So ultimately, what we have is, or because of this particular description, the reason we are able to arrive at this criteria, that is the overall change in the entropy for the cyclic process is 0. The reason we are able to arrive at this is primarily because we have described the change in the entropy for each step as the difference between entropy at the endpoint and the entropy at the initial point. So because we have described the change in the entropy in this manner, we are able to arrive at this criteria here that fulfills the initial criteria, that the overall change in the entropy during the cyclic process is 0. So what we can infer from this simplistic example here is the difference in, or the change in the entropy, it does not depend on the path, but irrespective of what the path is, but it depends on the state of the system. Again, only when you describe the change in the entropy for every step as the difference between the final and the initial state, you will be able to arrive at this criteria that characterizes a reversible process. So essentially, you begin with a reversible process, you express the change in the entropy during each step. So there are two steps that are involved, and you are describing change in the entropy at each step, and ultimately you arrive at a relation that indicates this is a reversible process. So you are proving this is a reversible process by considering the change in the entropy at each step. Now this proof is only possible when you calculate, or the way we express the change in the entropy at each step as the difference between the entropy at the final state minus the entropy at the initial state. So only when we give this characteristic description, this criterion is fulfilled. So essentially what we mean by that is, when we treat, or the way we express the entropy, or the way we estimate the entropy, and the way we arrive at this criteria, the way this criteria is derived, indicates that this entropy is not a path variable but a state variable. The change in the entropy is not a path variable but a state variable. So only when you treat the change in the entropy as a state variable, you will be able to show that the process which is occurring here is a cyclic process. Even though we construct a cyclic process and we arrive at a relation, this relation implicitly assumes that the change in the entropy is a state variable. Irrespective of it, even by just considering this expression here alone, we will be also able to state that the change in the entropy is a state variable. So let me repeat, just by considering, so we arrived at this expression here by purely from a theoretical standpoint and purely by understanding what a reversible process means. And this expression here gives us this relation, and this relation is indicative of the fact that the change in the entropy is a state variable, not a path variable. The same result, the same conclusion can be arrived by again considering a simplistic operation here, and here we arrive at the characteristic relation, that is the overall change in the entropy is 0, by expressing the change at each step, the change at an entropy at each step in a specific manner, and that specific way in which we express the change in the entropy at each step is indicative that the change in the entropy is not a path variable, it's a state variable. So essentially we consider a cyclic process, or we consider the cyclic process with several steps that are involved. We arrive at a specific or a defining characteristic relation, and from that characteristic relation you arrive at this particular expression here. This particular expression in itself describes that the change in the entropy is a state variable. However, this can further be affirmed by considering the simple cyclic process such as this, and by considering the change in the entropy for each of these steps, and by specific way of defining the change in the entropy for each of these steps, we arrive back at this characteristic expression. Now, by appropriately defining the change in the entropy at each step, we implicitly assume that the state variable or change in the entropy is a state variable. So therefore, ultimately, for a given process, the change in the entropy, or in a thermodynamic framework, the change in the entropy is a state variable. So far, what we have essentially considered is largely focusing on a specific aspect of a process, or a specific kind of a process. So far, all the discussion we have is rather restricted, or the stemming aspect for all the discussion we had was the Carnot cycle, and this Carnot cycle, if you could recollect, we made it into a cycle. Now, in our world, or in the physical world, often it is very rare for us to find a reversible process, and most of these processes are often irreversible in nature. Now, if you could recollect, while we introduced the concept of the entropy, the place where we introduced the concept of entropy, it was not in the context of a reversible process. So reversible process is rather a byproduct of our ultimate goal. Our ultimate goal is not to study the reversible process, but our ultimate goal is to study a spontaneous process, a irreversible process. Now, if you could recollect, when we introduced the concept of entropy, we wanted to, or when we want to understand, or when we want to get into the second law of thermodynamics, we were interested in understanding not the static state of the system, but the dynamic state of the system. This is how we began our discussion on the second law of thermodynamics. We wanted to know, or discuss, or describe the dynamic state of the system. Now, we saw that a system can be static, that is, it can stay at an equilibrium state forever, or the system is often dynamic. And when you consider a dynamic system, we assumed in our initial state that, or in initial discussion, that whenever we consider a dynamic system, this means a system is moving towards a new equilibrium. So it has started with a new stable state, and it's now moving towards a new stable state, a new equilibrium position, and this is the dynamic movement that we observe. So whenever we consider a system, there are two possibilities, static and dynamic. And dynamic means the system is moving towards a new equilibrium. Now, we have so far considered a reversible process, so it indicates that even though we see a dynamic system, it need not always be moving towards an irreversible, or it need not be always experiencing an irreversible change. It is possible for the system to have experience a reversible change as well. So let us go back to the starting point. So we categorize the state of the system as static and dynamic, and in our initial discussion we only consider the irreversible or the spontaneous process as the dynamic process. So if you could recollect, whenever we consider, or when we introduced or consider the system that is in dynamic process, we assumed that the dynamics, or this rather non-static nature of the system indicates that the system is moving towards a new equilibrium, meaning the system is spontaneously moving towards a new stable state. We did not consider a reversible process. However, when we move towards the operation of the heat engine, and translated it to the Carnot cycle, the relation that we have right now is for the reversible process. So we began our discussion with the irreversible process. Now we have arrived at a criteria for the irreversible process. The criteria for the irreversible process is the overall change in the entropy for a reversible process is 0. So using the second law of thermodynamics, we are now in a position. So when you see a dynamic process that is occurring to a system is experiencing a dynamic process, now using this criteria, you will be able to say if the changes that is experienced by the system, is it reversible or irreversible. So from the second law has attained some portion of its purpose, that is, it is possible through the second law for us to state by looking into a dynamic system to state that if the system is experiencing a reversible change or if it is experiencing an irreversible change. So this criteria here, which we arrived using the second law of thermodynamics, largely based on the second law of thermodynamics, now helps us understand if the dynamic system, helps us describe if the dynamic system which we are considering is experiencing a reversible change or an irreversible change. Now we have arrived at a criteria for the reversible change. So when the summation of the change in the entropy that is experienced by a dynamic system is not equal to 0, then what essentially it means is that the system is experiencing an irreversible change. So we have arrived at a criteria, and that criteria states the overall change in the entropy when the system is experiencing a reversible process is equal to 0. Now when it is not equal to 0, it is rather logical for us to state that then it is experiencing an irreversible process. Now not equal to 0, there are several possibilities associated with it. It can be greater than 0 or it can be lower or less than 0. So let us now see what is the criteria that dictates an irreversible change. So again, when you consider the definition of the irreversible or the spontaneous change, we mean the change in the state of the system from a old equilibrium to a new equilibrium, from an unstable state, from a non-equilibrium condition to an equilibrium condition, an unstable state to a stable state. So we want now to understand what is the criteria that dictates the change in the state of the system from an unstable state to a stable state. Now in order to do that, let us go back to our previous description of the simplistic expression from which we arrived at this expression here, the simplistic relation from which we arrived at this criteria here. So the simplistic expression from which we arrived at this criteria can be expressed as Q1 by T1 plus the minus of Q2 by T2 is equal to 0. Now essentially this expression considers heat that is fed into the system and heat that is removed from the system, that is heat that is lost by the system. Now this here indicates the heat that is fed into the system. So this is something that can be varied by us. You can consider any possibilities. You can consider any number of heat that can be fed into the system. Now for a reversible process, once you have fixed the input, then the output is fixed in order to ensure that this criteria is satisfied. So let me repeat. For the criteria for the reversible process to be satisfied, you need a heat input and the heat that is lost. Now once you fix the heat input, so whatever in our part, so whenever we are operating on a heat engine, it is our prerogative rather to choose whatever heat input we are feeding in. So once you fix the heat input, and assuming that the temperature in which this engine is operating is also fixed, then this term here is dependent on this heat input. So this heat that is lost is dependent on the heat input. So whatever heat that is lost during a reversible cycle, so is dependent on the heat input. So the changes that occurs during a reversible cycle is fixed by the criterion here. So you have to follow a fixed criteria in order to ensure that the process that you are observing is a reversible one. And for that process, when you fix the heat input, then the heat output is fixed. This is something that we need to be sure about. Now when we want to disturb this process, now when we want to change this process to a reversible, from a reversible one to an irreversible one, then only place where we can play around with is this here. Let me repeat. You have a reversible process, you have fixed the heat input. Now once you have fixed the heat input for a reversible process, because you have to fulfill a specific criteria here, then the heat output, the heat that is lost, is fixed. Now when you want to disturb this process, when you want to ensure, or when you want to rather compromise on the reversibility of the process, then one place you can change within the system, then one place we can change is when the heat that is lost by the system is disturbed. So whenever the heat that is lost by the system is disturbed, then what essentially you would have is you would have an irreversibility, this criteria being disturbed, and thereby an irreversibility being introduced. So essentially, when I consider this here, and so this relation so far is indicative, or it is a heat transfer that fulfills the reversibility criteria. Now in addition to that, if I include, say for instance, a Q bar 1 and T1, then what I'm essentially doing is I'm reducing the heat that is lost. I'm reducing the reversible change. So when I'm reducing the reversible change, then what I'm essentially introducing is a irreversible change. Let me repeat. When you have a reversible process, there is so whenever you have a reversible process with a fixed heat input, there needs to be a specific amount of heat output that is given out by the system. When the system fails to give out this specific amount of heat, then the system experiences an irreversible change. Now, numerically, during this derivation, when we want the system to give out not the required amount of heat to bring back the not the required amount of heat to complete the cycle, to make it completely reversible, then we need to reduce this term here. So this term, let me highlight it in red, this term needs to be reduced when we want to ensure that the heat that is lost does not bring about a complete reversal of the changes. So in order to reduce this term here, you are adding an additional term. You are adding an additional change. Now in this case, when you do that, then this criteria is not fulfilled. So this, by adding this term here, you are ensuring that the overall change is not equal to 0. There is some resultant change. So even though these two gets cancelled out, there is some resultant change. So let me repeat. For the operation for a reversible cycle, for a given heat input, there needs to be a specific output. There needs to be a specific amount of heat that is lost. Now, when you reduce the specific amount of heat that is lost, then you are not able to bring about, or you are not able to reverse the change. So let me consider, so let us consider the simplex cyclic case here. So you start with A, you feed in Q1, then the system moves to B. When you feed in Q2, or when the Q2 is removed, rather when the Q2 is removed from the system at B, the system goes back to its original state A. Now instead of removing Q2, you rather remove Q bar 2, which is less than Q2. Then what would happen is, when you have, instead of removing Q2, you remove Q bar 2, which is less than Q2, then the overall change that is brought about when the system moves from A to B is not completely reversed. The change is reversed only when Q2 amount of heat is removed. So when you remove just Q bar 2 amount of heat, the overall change is not reversed. The change, it will reach only up to this state here. So it will reach an A prime state here, and there is an irreversible change that has occurred in the system. So this irreversible change, in this case, in this simplistic example, how we have arrived at this irreversible change is by reducing the amount of heat that is lost by the system, and the same we have expressed here. So we have reduced the change that brings back the system to its original state. This change that brings back to the system to its original state is reduced by including a specific change. So this is reflected in this specific change. So essentially what we have is, we have an expression like this that indicates a process wherein the summation of all these terminology is not equal to 0. So essentially, we have already introduced these terms as the change in the entropy for the reversible process, and here we have introduced a change in the entropy that is for the irreversible process, and because of this summation the criteria is not fulfilled, and essentially what we end up having is an irreversible cycle. So we begin with a reversible cycle, and for that cycle to be reversible, whatever change is brought about by the heat input should be equal to that of the change that is brought about by the heat output. Since we have fixed the heat input, the change that is brought about by the heat output should only be varied in order to bring about any changes to this system. Now, in order to do that, we reduce the change that is brought about by the heat output. So we reduce the change that is brought about when the system wants to transfer or change from B to A. This we do that by adding a specific amount of a change, and this specific amount of the change, because of this expression here, we relate it or we refer to it as the change in the entropy or irreversible entropy. So now what we essentially have is, we have the change in the reversible entropy plus the change in the irreversible entropy, and this is not equal to 0. So we have Q1 by Q, other Q1 by T1 plus Q2 by T2. So minus of here, the minus is primarily because of the convention, and we have the irreversible change that is quantified by Q bar 1 by or Q bar 2 by T2, and this is not equal to 0. Now let us focus on this change here. Now when I want to increase the amount of irreversible change, then what I need to do is increase this change here. So increase this particular ratio here. So I have now a combination of an irreversible and an irreversible process. So I have a combination of a reversible and an irreversible process. The reversible process is expressed by the changes that occurs during the reversible process is expressed by this term here. The changes that occurs by the irreversible process is expressed here. So I have a complex process that includes both a reversible change and the irreversible change. The reversible change is accommodated by this term here. The irreversible change is accommodated by this term here. Now, when I want to increase the irreversible change, then I need to increase this particular ratio here. So this means, so this is already a positive number, and therefore when I want to increase the irreversible process, I need to increase this irreversible process or this particular ratio continually. So what this means is that when I want to add to, or when a system is experiencing a dynamic change, and in this dynamic change there is a reversible process that is occurring, that is irreversible process that is occurring, the degree of irreversible process, the amount of irreversible process, as the amount of irreversible process increases, this particular term here also increases. So this particular term, as it increases, what you essentially experience is the increase in the amount of irreversible change, the increase in the amount of irreversible process. So it means, so this term here, this term Q2 bar by T2 is greater than 0, and as it increases, the irreversible change also increases. So the criteria, the equality criteria for the reversible process is the overall change in the entropy for a reversible process is 0. Now when I want to arrive at the same criteria for the irreversible process, now from this relation I can state that when I increase, or when the amount of irreversibility increases, the overall change in the entropy also increases. So for the irreversible process, the overall change in the entropy is always greater than 0. So if it is equal to 0, then we end up having a reversible process. So we, based on this simplistic example and we considering a irreversible aspect to it, we are able to arrive at a criteria to describe an irreversible process. Now the irreversible process is possible, a process can be irreversible only when the associated entropies are increasing. So the irreversible process is associated with, or it is accompanied by, or it is driven by the increase in entropy. So as the entropy or the irreversible entropy increases, the irreversible change also increases. So that is what the criteria that is related to the irreversible change indicates. So the way we have arrived at this criteria is rather straightforward. Again, we considered a simplistic example. We began with a simplistic example and we wanted to introduce some amount of irreversibility to it. And this amount of irreversibility, we introduced it by considering the change or the heat that is lost, the change that is brought about by heat that is lost, because we are fixing the heat that is being fed in. And the degree of irreversibility depends on how much we are able to reduce the heat, that is the change that is brought about by the heat that is lost, and how much we are able to reduce this term depends on how much are we able to increase this term here. And this term here is what we refer to as the entropy change during the irreversible process. So this ultimately means that when we increase the entropy associated with the irreversible process, the more irreversible process we have. So supposing we have a system progressing from an unstable state to a stable state. When we have a system experiencing an irreversible process or irreversible change, what it means is that, so let us assume a process, let us assume a change in the state of the system wherein there is no reversibility that is involved. There is no reversibility that is involved. So all we are left with is this term here, and this term Q2 bar by T2. Again, because of our simplistic consideration, we have this description here. This needs to be increasing in order to increase the level of irreversibility. So that means, so this keeps on, so this should be greater than 0 and keep on increasing in order to ensure that the system is increasing in irreversibility. So that means we have now arrived at a criteria that dictates, that would help us characterize irreversible change in the state of the system. A change in the state of the system will be irreversible only when its corresponding entropy is always increasing. So there are two possibilities for a dynamic system two possibilities in which a dynamic the entropy associated with a dynamic system might change. One, this overall change in the entropy can be equal to 0. So in that case, the dynamic change that we are observing is a reversible change, or it can always be increasing. Now in that case, what we observe is an irreversible change. So from the second law of thermodynamics, we are now in a position to state, by looking at the dynamic system, we are now able to state what type of a dynamic system it is. Is it a reversible system or is it an irreversible system? For a reversible system, we essentially have no change, no overall change in the entropy. However, in case of an irreversible system or in an irreversible change that is experienced by the system, there is a continual increase in the change in entropy. So from this second law of thermodynamics has now given us two criteria to distinguish the dynamic nature of this system. So with this, I would like to wind this lecture up, and in the next lecture we will see the application of these criteria. Goodbye.